Yes, Table 310.16 can be used to determine the size of cables within a metallic covered cable tray. Now let's discuss whether you can put conductors of different sizes together in the same raceway. The answer is yes, you can. However, there are guidelines you must adhere to. Firstly, the ampacity of the raceway needs to be based on the largest conductor within the raceway. Secondly, the conductors should be grouped in a manner that promotes adequate heat dissipation. Thirdly, ensure the conductors are protected against physical damage. Now addressing the question of whether to follow Table B 310.11, which deals with adjustment factors considering 50% load diversity, the answer is no, you don't need to follow Table B 310.11 in your specific scenario. Table B 310.11 is applicable to conductors installed in a raceway that isn't fully loaded. Since you mentioned that the raceway is fully loaded, you should use the adjustment factors found in Table 310.15. B2. Here is a summary outlining the steps to take when sizing cables in a metallic covered cable tray. Step 1. Determine the required ampacity for the largest conductor that will be placed in the cable tray. Step 2. Consult Table 310.16 to ascertain the allowable ampacity of the cable tray itself. Step 3. Apply the relevant adjustment factors from Table 310.15. B2. Add to the cable tray's ampacity, accounting for factors such as the number of current carrying conductors. Step 4. Select a cable tray that possesses an ampacity rating equal to or exceeding the ampacity required by the conductors it will house. Considering these points ensures a safe and compliant installation. Going into more detail on Table 310.16, it is a crucial reference within the National Electrical Code, or NEC, offering ampacity values for insulated conductors rated up to 2000 volts, installed in raceways cables, or directly buried. These ampacity values are based on specific conditions such as an ambient temperature of 30 degrees Celsius, or 86 degrees Fahrenheit, and no more than 3 current carrying conductors in a raceway or cable. It is essential to understand that these values serve as a baseline. When actual conditions deviate from these baseline parameters, adjustments must be made to the ampacity values obtained from Table 310.16. Factors like higher ambient temperatures or a greater number of current carrying conductors can reduce the allowable ampacity of the conductors. The NEC provides specific adjustment factors and correction factors to account for these variations. The proper application of these factors ensures that conductors operate within their temperature ratings, preventing insulation degradation and potential fire hazards. For instance, if the ambient temperature exceeds 30 degrees Celsius, a temperature correction factor must be applied to reduce the allowable ampacity. Similarly, if there are more than 3 current carrying conductors in a raceway or cable, adjustment factors from Table 310.15 B2 must be applied. These adjustment factors decrease the ampacity based on the number of conductors, accounting for the increased heat generated. Now let's clarify the concept of current carrying conductors. A current carrying conductor is any conductor that carries electrical current under normal operating conditions. This typically includes phase conductors in a circuit. Neutral conductors may also be considered current carrying conductors under certain circumstances, such as when they carry significant harmonic currents in a 3-phase system. Grounding conductors, both equipment grounding conductors and grounding electrode conductors, are generally not considered current carrying conductors because they only carry current during fault conditions. Understanding which conductors are considered current carrying is crucial for accurately applying the adjustment factors in Table 310.15 B2. In your specific scenario, where you have a mix of conductor sizes, you correctly identified the need to consider the adjustment factors for having more than 3 current carrying conductors in a raceway. The 2005 NEC Table 310.15 B2 provides these adjustment factors, which reduce the allowable ampacity of the conductors based on the number of current carrying conductors in the raceway. It is important to note that these adjustment factors are cumulative. For example, If you have 7 to 9 current-carrying conductors, the ampacity must be reduced to 70% of the value listed in Table 310.16. This reduction accounts for the increased heat generated by the multiple conductors in close proximity. When applying these adjustment factors, it is essential to use the correct ampacity value from Table 310.16 as the starting point. This value is based on the conductor's insulation type and its size. Conductors with higher temperature ratings, such as 90 degrees Celsius rated conductors, generally have higher ampacity values than those with lower temperature ratings, such as 60 degrees Celsius rated conductors. However, the termination temperature rating of the equipment to which the conductors are connected must also be considered. The NEC generally requires that conductors be size-based on the lowest temperature rating of any connected termination conductor or device. This means that even if a conductor has a 90 degrees Celsius rating, it may need to be sized based on the 75 degrees Celsius or 60 degrees Celsius ampacity column in Table 310.16 if the terminations are only rated for those temperatures. Regarding the mixing of conductor sizes in a raceway, as you mentioned, having 3/0 AWG cables and 10 AWG cables, the NEC permits this practice, but it is critical to ensure that each conductor is protected according to its ampacity. The overcurrent protection device, such as a circuit breaker or fuse, must be sized to protect the smallest conductor in the raceway. This typically means that the overcurrent protection device will be sized to protect the 10 AWG conductors, as they will have a lower ampacity than the 3/0 AWG conductors. It is also important to consider the voltage drop in the conductors. Voltage drop is the reduction in voltage that occurs along the length of a conductor due to its impedance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. To minimize voltage drop, larger conductors may be required, especially for long runs or circuits with high current loads. You can calculate voltage drop using formulas that take into account the conductor's length, current, and impedance. Online voltage drop calculators are also available to simplify this process. In addition to ampacity, temperature ratings, and voltage drop, it is also essential to consider the physical fill of the raceway. The NEC specifies maximum fill percentages for raceways to ensure that conductors are not overcrowded, which can impede heat dissipation and make it difficult to pull conductors. The fill percentage is the ratio of the total cross-sectional area of all conductors in the raceway to the cross-sectional area of the raceway itself. Different types of raceways have different maximum fill percentages. For example, rigid metal conduit, or RMC, typically has a higher fill percentage than electrical metallic tubing, or ANT. The NEC provides tables that list the dimensions of various conductors and raceways, allowing you to calculate the fill percentage accurately. When mixing conductor sizes, it is important to use the correct dimensions for each conductor when calculating the fill percentage. Remember, you mentioned Table B 310.11. To reiterate, you don't need to apply Table B 310.11 in your scenario because it addresses raceways with conductors not fully loaded. Table B 310.11 provides adjustment factors that can be applied when the load on a raceway is diverse, meaning that not all conductors are carrying their full rated current simultaneously. This table allows for a higher overall ampacity in the raceway compared to when all conductors are fully loaded. However, since you stated that your raceway is fully loaded, Table B 310.11 is not applicable. Instead, you should use the adjustment factors in Table 310.15, B2a, which are designed for fully loaded raceways. Let's clarify the difference between ampacity and allowable ampacity. Ampacity refers to the current carrying capacity of a conductor in free air, while allowable ampacity is the ampacity of a conductor after applying all applicable correction and adjustment factors. The ampacity is a theoretical value based on the conductor's insulation type and size, while the allowable ampacity is the actual current that the conductor can safely carry under specific installation conditions. The NEC requires that conductors be sized based on their allowable ampacity, not their ampacity. This ensures that the conductors are protected under the actual operating conditions. It is essential to carefully consider all applicable correction and adjustment factors to determine the allowable ampacity accurately. Failure to do so can result in undersized conductors that overheat and potentially cause a fire. Now, concerning cable trays, the NEC defines a cable tray as a unit or assembly of units or sections and associated fittings forming a structural system used to securely fasten or support cables and raceways. Cable trays are commonly used in industrial and commercial applications to support large numbers of cables, providing an organized and accessible wiring system. Cable trays can be made of various materials, including steel, aluminum, and fiberglass. Metallic cable trays must be properly grounded to provide a safe path for fault current. The NEC specifies grounding requirements for cable trays in Article 392. Cable trays are available in several types, including ladder type, ventilated trough type, solid bottom type, and channel type. Ladder type cable trays have openings in the bottom, allowing for ventilation and easy access to the cables. Ventilated trough type cable trays have a ventilated bottom, providing some ventilation but less access than ladder type trays. Solid bottom type cable trays provide maximum support for the cables but offer the least ventilation. Channel type cable trays are typically used for supporting single runs of cables or tubing. When selecting a cable tray, it is essential to consider the weight and size of the cables it will support, the environmental conditions, and the accessibility requirements. The cable tray must be able to support the weight of the cables without excessive deflection. The environmental conditions, such as temperature, humidity, and exposure to chemicals, must be considered when selecting the cable tray material. The accessibility requirements will determine the type of cable tray that is more suitable. The NEC provides specific requirements for the installation of cables and cable trays in Article 392. These requirements cover topics such as cable securing, spacing, and support. Cables must be securely fastened to the cable tray to prevent movement and strain. The spacing between cables must be sufficient to allow for adequate ventilation. Cables must be supported at intervals specified in the NEC. When installing cables and cable trays, it is essential to follow the manufacturer's instructions and the NEC requirements carefully. This will ensure a safe and reliable installation. Let's talk about the use of metallic covered cable trays. Using metallic cable trays offers several benefits. Firstly, they provide excellent mechanical protection for the cables, shielding them from physical damage and environmental factors. Secondly, metallic cable trays can act as an equipment grounding conductor if properly installed and bonded, offering a low impedance path for fault currents. Thirdly, they provide a neat and organized way to support and manage a large number of cables, making maintenance and troubleshooting easier. However, there are also some considerations when using metallic cable trays. Metallic cable trays can be susceptible to corrosion, especially in harsh environments. Proper selection of materials and finishes is essential to prevent corrosion. Metallic cable trays can also be more expensive than non-metallic cable trays. Now about the specific cable sizes you mentioned, 3/0 AWG and 10 AWG, let's look at typical ampacities. Keep in mind that the exact ampacities depend on the insulation type and temperature rating of the conductors. However, as a general guideline, a 3/0 AWG copper conductor with a 75 degrees Celsius insulation rating typically has an ampacity of around 200 amps, according to table 310.16. A 10 AWG copper conductor with a 75 degrees Celsius insulation rating typically has an ampacity of around 30 amps, according to table 310.16. These ampacity values are for conductors installed in a raceway with no more than 3 current-carrying conductors. If there are more than 3 current-carrying conductors, the adjustment factors in table 310.15 V2 must be applied to reduce the allowable ampacity. When selecting overcurrent protection for a circuit with mixed conductor sizes, the overcurrent device must be sized to protect the smallest conductor. In your case, the 10 AWG conductors have a lower ampacity than the 3/0 AWG conductors, so the overcurrent device must be sized to protect the 10 AWG conductors. This typically means that the overcurrent device will be a 30 amp circuit breaker or fuse. The 3/0 AWG conductors will be protected by the same overcurrent device, even though they have a higher ampacity. This is because the overcurrent device is sized to protect the entire circuit, including the smallest conductors. One more thing to consider when mixing conductor sizes is the potential for circulating currents. Circulating currents can occur when conductors of different sizes are run in parallel in the same raceway. These currents can cause increased heating and reduce the overall efficiency of the circuit. To minimize circulating currents, it is recommended to use conductors of the same size and length when running them in parallel. If conductors of different sizes must be used, they should be installed in separate raceways. In summary, when sizing cables in a metallic covered cable tray, it is essential to follow the NEC requirements carefully. This includes considering the ampacity of the conductors, the temperature ratings of the conductors and terminations, a voltage drop, the raceway fill, and the overcurrent protection. By following these guidelines, you can ensure safe and reliable electrical installation.